In our previous analysis, we established a definitive conclusion about AI in financial markets. Using massive AI swarms for live trading is structurally broken. When thousands of AI agents interact, independent opinions vanish, a 73% variance collapse. Operational friction is severe. One simulation required 14 minutes and 80 million tokens. Annually, this costs $151,000, while a constrained 3-agent model accomplishes the exact same task for $1,080. Large interacting swarms generate expensive noise. Small, tightly constrained specialist teams generate trading alpha. Our data regarding execution speed and operational cost was flawless. We were entirely correct about trading, but our evaluation criteria for the tool itself missed the mark. If this architecture fails so completely at execution, it raises a mechanical paradox. Why does it continue to dominate the AI engineering landscape, and why are investors currently committing millions in funding to scale it? The answer requires us to stop evaluating the model based on strict financial execution and look at the specific domains where thousands of interacting agents produce results that no other method can replicate. MiroFish operates as a population behavior engine, simulating how collective belief shifts in response to new information. Academic evidence demonstrates a clear temporal gap in public discourse. There is a measurable lag between when a population forms a collective belief and when that belief translates into a physical market price movement. Mapping this consensus before it materializes in the real world offers a structural advantage that outlasts the millisecond edge of a trading algorithm. Massive swarms succeed in complex, emergent environments. These are domains where humans react to each other socially rather than making decisions in a vacuum. This split-screen diagram illustrates the difference in methodology. Traditional statistical models, like standard regressions on the left, treat individual data points as isolated and independent. Swarm simulations, on the right, treat them as reactive, influential nodes. The value comes from the emergent cascade effect. Agent 47's opinion shifts because it received a compelling argument, altering the belief of neighboring nodes, triggering a population-wide consensus shift by round 14. Public opinion polling illustrates the limitation of static measurement. A poll takes a rigid snapshot of what people say they believe at one specific moment. It cannot map how those beliefs mutate through social interaction over time. The flock vote architecture provides the alternative. Instead of using homogeneous logic, it instantiates AI agents with high-fidelity demographic profiles, encoding their age, income, education, and media consumption directly into their behavioral logic. When researchers inject a single news event into this simulated demographic network, they do not get a static number back. They observe a trajectory, detailing exactly how and why an electorate's voting intention shifts over simulated weeks. The socioverse system takes this to an extreme scale. It utilizes behavioral models derived directly from 10 million real-world user profiles to give its agents the statistical fingerprint of actual human behavior patterns. Capturing a dynamic trajectory of belief formation is structurally superior to taking a static snapshot. It allows analysts to watch the narrative move through a population before the real-world event has concluded. This exact dynamic applies to the highest stakes applications of multi-agent simulation, military wargaming, and nuclear crisis modeling. In a recent study at King's College London, researchers placed 3 leading large language models into a tournament of 21 distinct simulated nuclear crisis scenarios. Large language models, or LLMs, are AI architectures trained on massive text datasets to process and generate complex reasoning. The quantitative findings were severe. AI agents autonomously utilized nuclear signaling in 95% of the simulated crises. The true value of the simulation was the transparency of the process. The agents generated 780,000 words of structured reasoning across 329 turns of play, exposing the exact logical pathways from initial crisis to nuclear escalation. A parallel study at the University of Southern California demonstrated that agent swarms can autonomously coordinate disinformation campaigns. They amplify successful content and optimize posting patterns to generate massive grassroots movements without any human operators. This exposes a dual-use reality. The exact same network mechanics and persuasion loops that spread artificial propaganda govern how authentic human sentiment spreads. Because massive swarms authentically replicate human persuasion loops, they function as ideal computational laboratories. They allow analysts to model any form of social contagion by injecting a catalyst and watching the network react. When we connect this sociological modeling back to financial markets, we locate a specific, measurable time lag between public narrative and actual asset pricing. The Bank of Canada published the rigorous Macaulay-Song study in 2024 to map exactly how this phenomenon works. They found that media narratives independently shift social sentiment, entirely regardless of whether the underlying factual information about an asset has actually changed. The narrative itself acts as the causal mechanism. The Finbert Ensemble study proved this at scale. Finbert is a specialized natural language processing model optimized specifically for financial text analysis. By processing 50 million tweets across 2,557 companies, researchers proved that social sentiment has a directional, causal influence on stock returns. This animated timeline shows the four-stage cascade of market movement. First, a news event occurs. Second, competing interpretations cause sentiment to shift across networks. Third, a public consensus crystallizes. And finally, market participants position their trades and move the price. The critical temporal metric is the delay between node 3 and node 4. The gap between the narrative consensus crystallizing and the price actually moving takes 24 to 48 hours. Whoever can computationally map the narrative consensus first gains a guaranteed forward-looking indicator before the actual market has time to react. This forces a complete reevaluation of the MiroFish engine. It operates strictly as a leading indicator factory, designed specifically to exploit this 48-hour narrative-to-market lag. When an exogenous event occurs, the system's GraphRAG architecture activates. GraphRAG is a retrieval technique that builds structural knowledge graphs to map complex relationships between data points. It immediately extracts the entities of the event and seeds them into the swarm. MiroFish relies on a dual-platform simulation. It runs thousands of AI agents simultaneously across simulated versions of Twitter and Reddit, watching them debate, persuade, and form coalitions in real time. It avoids the variance collapse that ruins homogeneous swarms by using heterogeneous agents. Assigning distinct demographic personas and risk profiles to each agent is essential for modeling realistic social friction. In this context, the system's 14-minute runtime is no longer a liability. It is far too slow for sub-second trade execution, but it is incredibly fast when the goal is extracting a 48-hour forward prediction. Every architectural choice in MiroFish optimizes for one singular outcome: processing a shock event and outputting exactly what the real-world crowd will believe tomorrow. We can now link the massive predictive capability of the swarm with the fast, deterministic execution of a specialist framework, creating a single symbiotic pipeline. The massive swarm acts as the telescope, a broad tool used to simulate the 48-hour narrative trajectory and establish consensus direction. That output feeds into the specialist system, the rifle, a constrained $1,080 a year tool that processes the directional data and executes the trade in seconds. The fast, deterministic system gains a measurable edge when it is preloaded with the direction of the predicted narrative trajectory. These two AI architectures were never competitors. They are complementary halves of a predictive machine designed specifically to position ahead of the crowd. We can ground this entire theoretical framework in hard market reality by examining the origin story and recent valuation of MiroFish. The creator originally built a 2024 tool called BetaFish. It was a backward-looking analysis engine that strictly parsed what had already happened in online discourse. He then executed a massive architectural pivot. In just 10 days, he built MiroFish, changing the system from parsing the past to forward simulating the future. Billionaire Chen Tianqiao, a man who built his fortune analyzing digital population dynamics, instantly recognized this capability. Within 24 hours of seeing the demo, he committed a $4.1 million investment. This table shows that the predictive applications extend far beyond financial markets. If the system can simulate a market reaction, it can simulate the public reaction to a product recall, a policy design, or a military deployment. In an environment where narrative drives sentiment and sentiment drives price, the ability to predict collective belief is the primary signal. MiroFish provides the telescope to see that signal before the crowd catches up.